Welcome to lecture 14. We'll continue our discussion on expander-based codes. So we will sort of quickly recall towards the end of last lecture. So we were talking about these expander codes, which are those codes due to Sipser-Spielman. In particular, we were talking about the following important result. Due to them, it's sort of linear time decoding, linear time unique decoding. Of expander. Let's quickly go over this. Even in this one, we had, while discussing expander codes also, we talked about two types of expander codes. One was the expander codes which are based on unique expanders, expander graphs which have very good expansion. So Sipser-Spielman had come up with this, but at the time of their result, there were no such explicit constructions of such codes. So then we gave the expander codes based on just regular expanders, expanders which didn't expand, have unique, did not necessarily have unique expansion, and showed how to build expander codes based on both these constructions. But the linear time decoding, we gave it for the expanders based on unique. So we'll recall that, and we'll also show how the same thing can be extended to general expanders, the linear time decoding. So the first thing which we saw was codes based on unique expanders. In particular, we had this graph, which is the left side here. Set of variables, constraints. The graph, G. I'm going to go a little fast the first 5-10 minutes because this is a recall of last time. Size of L was n, that was a block length of the code. Size of R was m. These are the number of constraints we were enforcing. And we had said that the graph is CD regular. That is, the left side has regularity C, the right side has regularity B. And P and D were discrete constants first. And furthermore, the graph was a delta C times 1 minus epsilon expander. For some epsilon is 0. So that was the fact that epsilon was smaller than half was what made it a unique expander. Graph that we had, and based on this graph, we constructed the following code: P of G. It's a code sitting on the left side, the axis 0, 1 to the L. It just states that for all j in the right, so every constraint on the right side, arity of all its neighbors is E. That was the code which we had put up there. It was Gallagher's sort of function. And the main theorem which the two main things which we saw last time, both due to Sipser-Spielman, were the following. The rate of this code is just easy to understand. It's just each constraint drops a dimension, so the rate is just n minus m by n. The key things are the distance. So the first thing which Sipser-Spielman showed is if epsilon isn't, if it's a unique expander, then delta of C of G is greater than or equal to, actually delta, but delta which is the extent of expansion, but then we show you can do even little better than it. We actually got all the way up to 2 delta into 1 minus epsilon, if you recall last time. Then that was about distance. The next one was if epsilon was even smaller, then actually C of G is efficiently, in fact, linear time decodable. Linear time linearly decodable. It's not necessarily distances. That's not the distance I'm proxying the previous decodable. From delta to 1 minus 2 epsilon. Would you want me to go over the algorithm once more, or so let's quickly go over the algorithm. Okay. So is the statement of the theorem and the unclear?
So there is an epsilon gap between distance by 2 and
There's a gap between. So we don't yet know how to this one. But the point is we don't even know what the exact distance of this code is. So there is some distance I'm guaranteeing in the first item, and I'm doing something unique equivalent up to something smaller than half the whatever I guaranteed. But by the way, even what is stated in 1 is not. You can actually improve the distance guarantee in 1. So this is a very recent paper, it's a paper from last year or earlier this year, which shows that it's not, it's actually delta by epsilon rather than delta into 1 minus epsilon. So it's a very, this guarantee is weaker, therefore unique decodable is not all the way up to half the unique decoding radius. So this algorithm which I'm going to give you is only up to this point.
and this is the best.
This
is the best on radius.
So the point is, as you'll see in the second part, so there are algorithms in which you slightly modify the code. It will also be an expander based course, and we know how to do better for it. So I do not know which is the correct expander way, but I think it's open to find out the exact unique given algorithm all the way up to half the minimum distance. So ideally, what we would like is I would like to prove combined distance. I would like to just give an algorithm that proves up to a particular, say you can be uniquely decode up to a particular point, and hence the distance is twice that way. I don't have such a statement. So that's from the algorithm. The algorithm was this sort of a L R, and you sort of put in the algorithm goes through several iterations. It has candidate words. And the kth iteration, what you see is as xk1, xk2, xkn. So this is initialized to the received word. So the decoder is the following object. So the decoder is, and in fact, we write it in such a way so that today it will be explicit. This is a linear time decoder. So the input is a received word, which is R1 to Rn in 0, 1, and with promise that the distance of the input from the code is less than strictly smaller than delta into 1 minus 2. So fractional distance. Okay. And how does the algorithm works? So there's the first initialization phase. Initialization separate phase. Because of set k to 0, you set the initial string to be equal. Then for bookkeeping, we want to label for each constraint on the right. We want to find out if it is being satisfied or not satisfied. So if summation xi I in neighborhood of j is 0, label j as snap, else label j as unset. And then what we do, we just maintain for every left variable, we maintain for every left variable, we go ahead and look at its neighbors and find out which are the ones which are the unsat ones among its neighbors and which are the ones which are satisfied among its neighbors. Okay, so we need to do that for keeping also, so that we just write that down. So therefore, keep for each I in L, we initialize sat k of I to be j in gamma of I, j labeled sat. Unsat. This is the k space, but right now k is 1. J labeled. Labels have 2 L's or 1 L? 2. Okay. Then there's the big while loop, which keeps checking if this is this one. So we check, so while there exists a variable such that its number of unsat neighbors is larger, is strictly larger than number of its satisfied neighbors. What do we then go? We then go and flip the value of increment k, we increment it to k plus 1, xk of I prime, we set it to be xk minus 1 of I prime p, sorry, 1 minus this. I prime is not equal to I, and it's more, and for this particular variable, we go and flip. That's how we update the thing. But in addition to that, what we also do is, so notice that this, look at this. So this, what we have updated is we have flipped this variable. We have flipped the value of this variable. Now, this is going to affect the sat and unsat of a whole bunch of guys. Which guys is it going to affect? All the red guys are going to turn into green, and all the green guys are going to turn into this one. So only those are the only guys who will change in sat and unsat. But this in particular will change several other guys sat I and unsat I. So you have to take a two-step walk from the vertex I. You have to go to its neighbors j, and then take its neighbors I prime, and all of them will, their sat or unsat will change by with some value. So you'll have to go and update. At this point, we go and update. Update sat k of I prime and unsat k of I prime for all prime. Strictly speaking, I do it for everything, but to just keeping, you know that the only I primes that will change are the ones which are distance 2 from. The rest will be unaffected. For all I prime, such that the usual graphical distance between I and I prime is go ahead and change all of them, and this was the final loop, and finally we return. So this is basically, so this is all these set of this neighborhood of. This is gamma of I. Yeah, so we did the correctness. So let's just quickly see why is this algorithm linear time. For that, let's make a couple of claims. Claims which should go through for correctness, and I'm going to define a few quantities. One, we'll define sat at k. This is the number of satisfied vertices of k. It's just going to be the union over all j in R, sorry, j in I. This is just for the analysis. I don't need this. This is just all the that. It's just a union of all the green vertices on the right, and similarly set k and set one. Let's do that. Then, since the distance guarantee which we have delta into, so we said that the 4 is Paschen distance so much away, we know that that is less than half of the distance which we have proved. We already proved that the 4 does this distance, therefore, and this quantity, this is just the fact that 1 minus 2 epsilon is less than 1 minus epsilon. Because of this, if there is a code word, it's a unique code word. They can't be two good. There is at most one C in CG such that delta of R C of G is less than delta into 1 minus 2 epsilon. Let's refer to that as 1 and let SK the step B those I in L so that at the kth iteration xk of I is not equal to T of L. Our hope is, our final goal is SK when the algorithm terminates is the empty set. You actually return the code. From plane 0, which you want to make, is actually plane. Notice that the plane 0 first is the guarantee. The first plane is about SK. So S0, we just been guaranteed that this is less than delta into 1 minus 2 epsilon. Okay. That's the claim. What's the other claim we know? We know at each step SK is just changing by 1. Therefore, you furthermore, this is another thing. For all k, size of SK minus size of SK minus 1 is equal to 1. You make only a change of 1. Either it increases or decreases. You could be, the flip could have actually been in the wrong direction. That's this is the claim 0 is a trivial observation. Both part 1 and part 2 are sort of trivial observations. What do we know about the other part? The other part is I want to say, let's look at unsat at 0. How many pairs can be unsatisfied at 0? At most n pairs. So this is certainly less than or equal to m. But notice the way the algorithm is proceeding, it always reduces the number of unsatisfied constraints on the right, because it's always taking a variable who has more left. Therefore, you always have this feature that unsat of k plus 1 is strictly smaller than unsat of k, and so on. Cannot go. It's the number, therefore that has to be a number. It's an integral. So this is claim 1. Claim 1 is just observation. But claim 1 will tell you that, just the second item in claim 1 will tell you that the number of iterations the while loop can go through is at most n, because each time unsat is decreasing, unsat has only, it starts off with the max value of at most m, that can only go almost n times. And C and D are constants for us, therefore the number of iterations for the while loop is a linear number. M is a linearly related to n. In fact, m is strictly smaller than m, so the number of iterations of the right side of this loop is linear. So to show that it is constant time, to show that the whole algorithm is linear time, it suffices to show that initialization phase is linear time, and each iteration of the while loop can be performed in constant time. So let's look at that. Is the initialization linear? I want to claim everything about the initialization is a linear time. Of course, the first two are easy. The second one is, this is because the degree is constant, this is a linear phase. And now furthermore, this one is also linear, because for each vertex, you look up that, you fill this up. So this is linear. So the initialization phase is linear. What about this one? So let's look at the while loop. So how do you, the while loop I claim, once you identify the I, then the update is easy. This update is easy. Don't think of this as rewriting a whole string. You just have one XK string and you go and modify it. So you don't have to copy the whole thing. This one is just, you only modify this part. And this update is, it's a, for how many guys you have to do this? All guys are I prime, this is at most C times 3 guys. Therefore, this is also constant. The only caveat is, can I identify which is the I that has this property? So for this, we maintain the sort of a queue structure in which you can get the what you do is, in addition, one other bookkeeping you do for every vertex you go there, you just go and maintain also whether the unsat is larger than the sat. Just maintain that, and the first time you fill it, just put that as and so maintain. So also, one thing which you want to do is maintain a list of This is something. This is just it's to ensure linear time. It's not for correctness of algorithm. Maintain list queue of variables such that unsat I is greater than sat I. Just maintain that list. That's some list you can, in the initial phase, that's fine. You can do that in linear time. Now, when you do this, you know only these guys, this one. For each of them, go and find out whether it has changed or not, and go and modify, update the list. So this is only done for checking linear time. Update list. So that the statement just changes to while queue is non-empty. That's fine. Okay. So this will tell you that the entire phase algorithm is linear time. And
no, I was just thinking.
yeah. Okay. And the proof of correctness followed by these two claims. If anyone wants, we can reprove it, otherwise I'll just get it. The first claim was the fact that This was where epsilon we needed it to be smaller. If epsilon is between 0 and 1/4, and Sk had not yet touched 0. Sk was greater than 0, but it was not too large. It was simply smaller than delta n. Then there does exist. Notice the while loop, for it to happen, the while loop doesn't say as long as Sk is not empty, it is going to do. It needs a variable for which it sees more unsatisfied neighbors and satisfied. It could be the case that you are in a very word in which it's not a code word, but every guy sees more satisfied neighbors than unsatisfied. That could be the case. But I want to claim that's not the case. There exists a I in L such that unsat of K of I is greater than sat of K of I. So this says as long as the distance from the code, the required final code word, target code word C has not gone larger, is not equal to delta n or more, you will always find a vertex at which you can make this progress. So claim 1. We proved this claim last time, and then claim 2 was taking. Notice this is true in the beginning phase. The beginning phase, in fact, S0 is even smaller than delta, it's delta into 1 minus 2 epsilon. But we didn't have a guarantee that size of Sk is monotonically decreasing. It could go up and down. So there might be times in which you're actually drifting away from the code word in the process. What we wanted to say is even if you drift that, you could not have drifted too far. Because we use the fact that the initial code word, the fact that S0 was larger, was not too large. This was that for all k, size of Sk is smaller than that. So at no step do you go too far, and so at every step you can make progress, and you know that the algorithm cannot go on indefinitely, it can go at most, and therefore eventually it has to stop. And so the only condition for it to stop is Sk being 0, the size of Sk being 0. But otherwise it will always make progress. Therefore Sk being 0, it's find out from the code. Okay. So do you want me to go over the proofs of claim 1 and 2, or this is exactly what was done from last time? So yeah, okay. So proofs from last time. Now, what we do? So this is so much for expander codes based on unique expanders, on expander graphs which had very good expansion. Now we go on to expander codes for codes from codes based on expanders. Not necessarily unique expanders. Here we did a couple of constructions. We given 2 constructions. I talk about one construction. I will also slightly modify the construction, talk about linear time decoding, because the modification works nicer. The other one also will work. So what was the construction we said? Here the ingredients were, we are given a graph G. The input was G. It's a B-regular graph. And it was a lambda spectral experiment. The second eigenvalue. Well, what did I mean by this? This is the fact that just this, that is 1 is equal to lambda 1 is larger than or equal to lambda, which is smaller than lambda 2, all the way up to lambda n, which is larger than minus lambda, which is larger than. 1. This is all that it means. There. Lambda 1, lambda 2, lambda n are the eigenvalues. Normalized. This is clear what I mean by this. So take the adjacency matrix, normalize it. So the adjacency matrix has ones if I and j are connected and 0 otherwise. Normalize it, that is divided by t. It's a regular graph. You had divided by the vertex of the starting point, but here every vertex is regular. So just divide every entry by t. And now look at the eigenspectrum of this. This is a real symmetric matrix. Therefore, it has a eigenbase. This is where you return it in linear algebra. It has an eigenbasis and all the eigenvalues are in fact real. So let's call, and it's not hard to see that the largest eigenvalue will be, there will be an eigenvalue of like 1, which corresponds to the eigenvector or the all ones eigenvector. And the smallest eigenvalue cannot be smaller than -1. The eigenvalues are going to be between 1 and -1. And now then, so the other eigenvalues lambda 2 to lambda n are sandwiched between 1 and -1. I want to say that lambda 2 is not more than lambda. And similarly, lambda n is not more than -1. So as long as this happens, as long as all the other eigenvalues are sandwiched between lambda and minus lambda, you're going to call this a lambda spectral expander. So that was the ingredient. That was, we will see the magical property of this. The key property of such a thing will be how we're going to use this is via the expander mixing lemma as stated. Normally we'll use that at least 3 times today in today's lecture. And then we wanted the small code. C0 is a code sitting on T. Let's make it a linear code. This is code sitting on T, D, R naught D, and delta naught D. It's a constant size code with rate R naught and delta. And the only requirement for us will be the condition that R naught should be greater than half and delta naught should be greater than half. Based on this, we have defined this code C of G comma C naught. Set of all X is now residing on the edges of the code. And we said that for all B in P, if you look at XT, these are 8 neighbors incident at I. Sorry, not summation X. Just XC, E, and E is incident of I. This D length vector should be a member of C naught. This is so we are looking at this, what's happening over here. We're looking at this one guy, it has D neighbors. That what you see over here should be a member of the small code. Notice that for in the case of the unique expander case, what is now when I say it's a member of C naught, I must tell you what order I'm going to do this. In the case when I previously said sums to 0, it doesn't matter which order. So here we are stating that it is a member of C naught, given that this is the ordering of the vertices. Choose an arbitrary ordering for every vertex separately, arbitrary ordering from 1 to D, and then when the thing is written that way, it looks like that. That's all I know. It's completely arbitrary. Fair enough. This was the construction we have said, and once again the theorem due to Sipser-Spielman, which we quoted last time, following the theorem. Says that the rate of this code, I don't know if I proved any of this in class, I don't think I proved either of them in class, is at least 2 R naught minus 1. And the distance of this code is at least delta naught into delta naught minus lambda. We didn't prove either of these. This will actually be in your homework, in your third problem set. So informally, what does this say? Informally, the expander lifts. So the small code had rate R naught and delta naught. It sort of lifts, and that were constants. It sort of lifts the goodness of the constant size code to this larger code. So it lifts the goodness of the constant size code to larger. This is just an informal. The reason I'm stating this, we'll see more examples of this in the second part of today's lecture. Yes. This theorem I will not prove. This theorem will be, therefore, you will see this in the proof of the in the homework. But what I want to state is what's the main tool that's used to prove this theorem. This is what will be called the expander mixing. What is the property of spectral expansion? What is the expander mixing? Once again, you're given, so G is a graph, V equals VE is a graph. Let's say it's a lambda spectral expander. That means when you view the normalized adjacency matrix of this graph, because the first eigenvalue is sitting at 1, stating that all the other eigenvalues are sandwiched between lambda and minus lambda. Now the expander mixing lemma is this amazing. This one, let's say. So let take any two sets, S and T, the vertices. So S and T are any. So S is one set, P is possibly an overlapping set. What we will look at is we look at the number. Let's pick an edge at random. Now, when I say an edge at random, I'll define what's the process. So I pick a vertex at random and pick a neighbor of it at random. So notice this is a directed edge because it says you what's the starting point of an edge. Even though the graph is undirected, it's a directed edge because the process is picking an edge, first of all, vertex, an endpoint of the edge, and then picking a random neighbor of it. So there's an initial I and a j. So let's look at this process. So I'm going to look at probability, which you pick I uniformly at random from B, and j uniformly, so this is uniformly at random, and j uniformly random from the neighbors of them. And then I'm going to ask what's the probability that ij, this pair, now it's a pair, notice it's an ordered pair, it's not an unordered pair. An edge is usually an unordered pair, but here I'm looking at it as an ordered pair. What is the one that this pair is in S cross T. Okay? So this is, now let's think of, I want to say the expand mixing lemma sort of trying to tell you how good the graph is as a random graph. So what would this quantity be for a random graph? What is the problem? Huh? No, for a completely so I want to just say
qualitative. I is less.
Yeah, I is a problem. It's the density of S times the density of T. So just let's write this. It is just minus. I'm going to say this is what happens for a. This is what exactly happens for a completely random graph. I want to say this difference is actually very small. And how small is it? It's governed by how small lambda is. If lambda is 0, this difference will be 0. The smaller lambda is, this difference will be. So this difference is going to be, the expander mixing lemma basically states that this quantity is less than lambda times Usually they just put a lambda and drop it, but it'd be useful to have this extra f. What is the other one? The other one is some number less than 1. It's usually mu of s, mu of t, 1 minus mu of s, 1 minus mu of t.
So what's exactly the quantity mu?
So mu is just the density of, it's just size of s by total number of vertices. Where mu of s is mod s. The reason I'm stating it this way is this is also true for some sort of weighted graphs where mu refers, so it's not modest by n. So the expander mixing lemma will remain unchanged. It is the definition of mu will change based on. You could have weighted edges. You can have edges which are right now all edges have equal weight. If you have weighted edges, the weight of a vertex will be proportional to the sum of the edges going weights of the edges, sum of the weights of the edges leaving it. Here all edges have equal weight because of the fact that it's a regular graph and it's a regular graph and all the weights edges are unweighted. So the expander mixing lemma is this. And this is sort of, people write expander mixing lemma in different forms, but I find this is the most convenient form to remember. Remember this random experiment. There is pick a random vertex and a random edge going out of it, and you're asking what's the probability that this pair is an element from S cross T. Notice edges which are completely in S and T will appear twice in this, because once I could have been the left endpoint or once J could have been the right endpoint. And then look at the difference with what happens if the graph are a completely random graphs. That's mu s times mu t, and that difference is at most this one. This is what the expander mixing lemma states, and the proof of that, the distance property just follows from the expander mixing lemma. What you will have in your third problem set is they will actually break up the proof of the expander mixing lemma into parts. When one of the problems you will do the expander mixing lemma. In the other part, you will use the EML. Given the EML, you will prove the distance statement. Okay. Expander mixing lemma is a very, very powerful statement, and we'll see the power of it later further in the class. Of course, it's used for this particular thing. We will see it. There will be at least 1 or 2 or more applications by the end of today's lecture. So okay. Questions on the expander mixing lemma. Notice once again the edges which have only one endpoint are counted only once in this. Edges which have 2 endpoints which are in the S intersection T are being counted twice in this because of the directedness of these edges. So I want to just also just like I did prove this, I want to ask what about the proof of decoding complexity of these standard systems. So Sipser-Spielman, what did Sipser-Spielman prove? So Sipser-Spielman proved for these particular things, Sipser-Spielman. They showed that linear time decoding if number of errors is even less than half we proved some notion of distance. The question is, can you go up after they were not able to prove half of it, much smaller. What they were able to show is when delta naught, delta naught square by 48 times up to some constant distance, but not all the way up to what we know is at least the unique decoding radius. This is the original paper of Sipser-Spielman. What we will show today is actually a construction due to Zemor. He changes the code a little bit. It will be basically the same code. We change the code a little bit. Slight variant of our construction. In order to give a very simple algorithm, and there he manages to show linear time decoding, number of errors is less than delta naught square by 4. Watch. So once again, I will not do this, but I will I'll actually give you the algorithm to show how simple the algorithm is. So firstly, I'll tell you what the variant he is going to consider, and then also tell you. The variant, what you do is, he'll take the expander graph as we said this, but then from this he will construct what's called the double cover. And the reason I want to do it is, double cover is something which you will see. There's a notion that it will be useful to have. So we given a graph, we will define what the
N is not there.
huh?
N.
There is an N. N is always the number, is a block length, which in this case will be the N is the block length. Here is also the number of vertices. Sorry, N will, so it's not the number of vertices, it's the number of edges. It's the one where the code is sitting on. So double cover graph. I give you a graph, say GB, comma E. The double cover is defined as double cover is a graph, is a bipartite graph. And so I tell you what's the left side, what's the right side. So the left side and right side are both copies of the original vertex. The vertex that is put. So the same vertex that is put on the left side, same vertex that is put on the right. So in other words, we can say it is sort of like it's B cross 1 and B cross 2. So there are two copies of this is just indexed with 1, these are just indexed with 2. B cross 1, B cross 2. And is a bipartite graph, let's say with bipartite graph with L being equal to B cross 1, R being equal to B cross 2. So these are identical copies of the two vertices. And when you put an edge, so now you have the same, you have B cross 1 over here, cross 2 over here. I had a graph and I had just B here. This is the original graph. So suppose I have edge UB here. Then what I'm going to do is now it's going to be bipartite graph, so that UB can either be U1, V2, or it can be V1, U2. Basically, those are for every such edge, we'll add both these edges. That's all. And for all UB belonging to the edges of the original graph, the double cover is a bipartite graph with L, R, and F. We have U, 1 and B, 2. This belongs to F, as well as B, 1 and U, 2. So you add both these. Right? So there's two copies. There's U1, there's V1, there's U2, there's V2. That's the double cover graph. Notice the double cover maintains the degree of the graph. The number of edges is number of vertices is doubled, the number of edges is also doubled. Every edge appears twice. What Zemor does is, if G were a spectral expander, he takes a spectral expander and instead of constructing the Tanner graph on G, he constructs the Tanner graph on the double cover of G. So the same C0 code. C0 code, there was decided on every vertex had B neighbors. Here also every vertex has B neighbors. We'll put the same C0 code. So it's going to be what Zemor does is just put the double. Take the same union expander graph. Instead of constructing the code on the edges here, he's going to construct the code on the edges here. Therefore, the actual number of edges is twice the number of edges. Here, the block length is actually 2 times the block length. But the base code constant says so for C0 is the same C0 code. So Zemor is just exactly does the same construction, the same graph construction, but instead of using the this graph, he uses a double cover. And what is Zemor? So Zemor's construction is the following. Zemor's construction. G is a spectral expander. GVE lambda spectral expander. P regular. C0 is as before, it's a D R naught D delta naught D to 4 with R naught greater than half and delta naught greater than that. Then Zemor of G comma C0 is exactly what we had considered as C of the double cover of edges. Okay. Why did we do this? Because there's something nice about the reason defined it this way is the decoding algorithm becomes very clean for this. What the decoding algorithm we gave? So the graph is sitting like this. Left side and right side this time are both this is B cross 1, B cross 2. You have edges going across like this. The edges always appear in crosses, and the received word is sitting on these edges. Notice the received word, it doesn't have to be that what is on this edge has to be on this edge. That's no requirement. Received word is sitting on this. I have to correct it. As there are not too many errors, I have to correct it. One. So he defines what is called a left decoding process and a right decoding process. Sorry, a left fix and a right fix. So each iteration in our previous loop, there was picked a vertex. There's going to be a left. There's going to be a left face. And what's the left face going to be? I'm going to take all the vertices from here, look at their neighbors. You have a particular word. What you need to see is you need to see what the local view of this vertex should be from C0. If it is C0, you don't fix it. If it is not C0, you just go and change it to the closest member in C0 that you can see. So left faces for all vertices in L, modify XE, E adjacent on B to the closest code word C in C0 that minimizes delta XE Notice they might not, if only if this distance is less than half the distance of the code word, will there be a unique such way? They might be otherwise multiple. The multiple, just pick one arbitrarily and put it. So left face, but you can also ask, do these things actually interfere with each other? That is, one vertex I'm doing modification, does it not? Notice it does not, because I'm modifying all things incident on this vertex. Then I'm modifying all things incident on this vertex. These two certainly don't share an edge. Therefore, this the left face does it parallelly on all the guys on the left hand point. And similarly, there's a right face. So it just makes these fixed. So it runs, and Zemor's algorithm is just the following algorithm. Give me a received word, run the left face, run the right face, run the left face, run the right face. Do this for log n times. At the end of this, if the original number of errors are not too much, this would have just fixed all the errors, and you would have gone to the closest code. The Zemor decoder is the following. You want to do this, but this once again uses the for a log n times. The log of size of vertices number of times.
What is A?
A is a large constant, which is dependent on the analysis. A is large constant, not dependent on the graph, a large universal constant.
It depends on the degree.
No, it doesn't depend on the degree. I don't think it depends on the degree. It's independent. Now let's face. And right face. One after the other. That's the interface. That's Zemo's algorithm and manage. And you can also show that right now the way the algorithm is said, it runs in n log n time because each phase requires n time. It's n log n, but you can be very careful, do the bookkeeping that such that the whole algorithm runs only in n time. You can check, you can modify, you can keep certain, just like we call this algorithm also the original algorithm we saw here. The natural algorithm, you have to search, but to find the I, you have to actually do a linear time search. But if you maintain the list queue, you can get the I very fast. So similarly, we'll keep some other extra variables around just to reduce the time from n log n to n. You can do this one. But this has another advantage. It's also a very parallel algorithm. So if you look at it in terms of parallel things, it's just a log n. This one, because all of the left face can be done completely in parallel. The left face for all the n vertices, you just run them in parallel, fix it. The left face, the right face runs in parallel. So you have just log n. With the entire decoding, if you look at it as a circuit, the depth of the circuit is only log n. The depth circuit is not a very deep circuit. Okay. So Zemor, once again, I will not prove this. The proof of this uses the expander mixing lemma. What I wanted to do, probably time. So I have another 25 minutes. So I wanted to talk another topic called distance amplification. Another quite an amazing application of expanders towards codes.
So I have a question
Sure.
about this construction. So how is it with right?
So the rate of actually I mentioned the rate of this. The Zemor's construction will be. No, so the rate is just the rate just is the same, will follow similar to this one. What do we have? The rate of it is 2R0. For any panel construction, with the base code as rate R0, this will be 2R0 minus 1. So this will also be 2R0 minus 1. So it will require a little work which I haven't done. This is what I mean. What you're asking.
Like this double cover construction.
The rate of ZGC0 will be at least 2R0 minus 1, and the distance of it will also be exactly what was before. It will be delta naught.
Radius dimension minus number of constants.
What?
So here also radius there are linear dependencies.
Yeah.
Yeah, here also radius dimension minus
Number of constraints. Yeah, that's the how we approve 2R0 minus 1. We have not used. There could be there could be more dependencies, and this could be a very loose way of counting it, but I'm not. notice that this dependency depends. Now, when you talk about dependence, then it matters how you are reading the code word. So right now I said arbitrarily for every vertex decide 1 to d in some order, and that's the order in which you see now. To understand dependencies, you have to say if this vertex I'm reading this way, this vertex I have to read it this way. You have to put all those and then understand dependencies. Right now I'm saying don't do any of that. Without that itself, you can get this. Topic is going to be what we call distance amplification. So far, we never seen this. Every process that we saw reduces distance. Concatenation, you do it as one. The tensor product of code reduces distance. The only way we could get very good distance was by going to a code over a large alphabet. Read-Solomon codes gave you this. In fact, here also we'll go to a large alphabet to get distance, but we'll show how expanded code. You give me a code with a particular distance, I will use expansion to go to a code over a slightly larger alphabet, but I will use expansion to go through the code over the larger alphabet. So actually a beautiful construction you do. You'll see two constructions. They will be very related construction. We'll initially see a construction. We'll see two constructions. Both using expanders, but using bipartite expanders. One is due to, the first one is due to Alon-Bruck-Naor-Naor-Roth. Construction, and then for the strengthening of this alone. Graph which we are looking at is a FRE with size of F equal to size of R, size equal to N. So this is sort of a unbalanced bipartite expander. It will be a lambda spectral expander. What do I mean by that? Once again, for a graph, I said for a graph something, what does it mean to be lambda spectral expander? You knock off the largest eigenvalue 1, all the other eigenvalues are in the range lambda to minus lambda. That's what it means to be a lambda spectral expander. If a graph is bipartite, it will have the -1. You can show that if a graph is a bipartite graph, it will always have a -1 as an eigenvalue. In fact, what you can show is that the eigenspectrum is sort of symmetric about the origin. If it has a particular value, lambda as an eigenvalue, it will have minus lambda also as an eigenvalue. You can easily show that if there's one eigenvector which witnesses lambda as an eigenvalue, you can produce another eigenvector which witnesses minus lambda as an eigenvector. So the eigenspectrum of a bipartite graph will be symmetric. So what do I mean by lambda spectral expander? So knock off the 1 and knock off the -1 of the two things. The rest of the eigenspectrum is sandwiched between lambda and -1. That's what it is. And there is a similar expander mixing lemma for this also. What is expander mixing lemma? Now the edges are going only between different. So for any set S on the right side and any set T on the right side, you are looking at, if you pick a random edge, that is pick a vertex on the right, for any set S and for any set T, now pick a random edge. What's the probability that the right end point falls into S and the left end point, or rather the left end point falls into S and the right end point falls into T? Compare it to what happens if you had picked it at random. And this will you get is the exact same statement as this. So we're going to work with lambda square this, and we're going to have a code C, which is on let's we call it the code C, the subset of its block length is n. Therefore, the code is residing on this one. Block length is n. Its rate is c r times n. Distance is delta times n. For convenience, let's think of it. For now, let me think of it as a Boolean code, but this would have worked over any answer. So, based on these two, I'm going to sort of construct a new code, which is going to have considerably. So I've given you a bipartite expander. Notice C is not a constant size code like in the previous case. Okay? C is a large code. Question is, from one large code, we'll construct another large code which has better distance, but over a slightly larger alphabet. So, what's one natural thing to do? Take any code word, C1, C2. I'm going to put the. You can label these vertices with the code. And let's also assume that this guy is speed. What do the AV and RNR process do? So they say, look at
Deregulate from both sides.
huh?
Deregulate.
It's a endless model is the model. Yeah, so I'm going to say direct. So when the graph is balanced, I'm going to say it's regular on both sides. So it's DD regular in our language, but because of the left it's a balanced thing, I mean irregular, I mean balance on both sides. And that's important for us. I want it to be irregular on both sides. So you have, so I'm going to say, give me a code word from this code, and I will produce a code word from the code that I want to construct. How is that going to be? First, they give me a code word, you will label all the left endpoints with this code word. Now just push these symbols. Here, the symbols are on the vertices. Just push them on the edges to the other side. Therefore, this as a particular symbol here, this symbol here, over here will get pushed along this edge, along this edge, along this edge, along this edge. It's going to get pushed along all of the edges. And these vertices now will collect these. They will collect these sort of symbols from this. So each vertex here collects these symbols. The final code, which we call, which I'm going to call ABNRR GFC, this code is going to be X in 01D to the alphabet is going to be 01D to the end, and to writing it is going to be a pain, but it should be clear what it means. I'm just going to send these codes across along these edges, collect them there, and now that, so the code will now, the alphabet will be blown up by B. What you write is you write this object. The symbol which I'm going to write here, if its neighbors were 1, 5, 7, 8, and 10, the thing what I'm going to write here is C1, C5, C7, C8, and C10. Okay, so that's going. So this is a pi regular graph. So the alphabet has grown from being of size q to becomes q power 5. So is the construction clear? So what is this thing? What I'm saying? So let's write this formally over here. So I'm going to write this way. It just states that there exists a C equals C1, C2, Cn in this code such that X, so this is Xj, the ith location of this, so xj, so the jth vertex, ith location, what should it be? It should exactly be the C at the gamma ith neighbor of J. So if there exists one single code word such that this happens, this is just a representation. Remember, forget about this definition. That's the picture is. You take a code word right on the left side, push the symbols across, and collect it over here. So now it's become a code of a larger alphabet. I want to claim that this code which I've done it, because of the underlying properties of the expanded graph, this new code is actually an extremely good code with respect to distance. Rate, of course, would have deteriorated. Let's look at both those. Let's try to understand. Is the definition of the code clear?
You by good you mean near GB1?
No, I don't mean near GB1. All I'm going to say is the distance becomes the alphabet has changed. I want to say it is just good by good. Good, I just mean I'm going to just mean that the distance has amplified a lot. So we will to know how well it goes towards GB1, we need to understand how good the expander is graph is. And so far we have never done that. We have never understood what are the best expanders and stuff. So we will not do that in this course. We can do that also for all of these objects. What I want to just ask is, what's the rate? Let's first ask a simple question. What's the rate of this code? By the way, is this a linear code? If I take two code words, if I add it, will I get?
Yes.
Yeah, if I take two code, if I add it, I get the code word because this process is the same thing as adding the two code words on that. But linear means one more thing. Linear means you have to also respect scalar multiplication. Now, what is a scalar you are going to multiply it with? Typically, the alphabet. So for that, you need to think of this as a field and multiply by those this one. It's completely unclear whether it is this one. So it's not linear. In fact, I don't think it is linear with respect to, if you think of this as a field, why the hell should it respect the properties of that field? That field doesn't enter in this picture at all. So think of this as a code in which the alphabet is not coming from the large field. Don't even think of the large field at all. It's just these symbols in the small field, and it's linear over the small field. We have never defined these sort of linear codes so far. That is, at every location, you don't give an element from a field, you give d elements from a field. At every location, you give d elements from a field, and it is linear with respect to that field, not from this f to the d. So there is no f to the, there is no q to the d field in this construction, and we never talk about it. It's a linear code. We have never encountered such things, except if you have done the problem set, you would have encountered it. The polynomial based codes which I did, the multiplicity code, the folded resolvent codes, all of them belong to this. That is, at every location, you don't give one field element, you give yes field elements, and it's linear with respect to the small field, not with respect to the SQ to the S or so. So there are instances of course, it's going to be linear with respect to the just the field, in this case 0, 1, not with respect. There is the other field 0, 1 to the D is not a field at all. It never comes in this construction naturally, so we'll never talk about it.
Here, if I concatenate the code by some error correcting code, then it will become linear.
What do you mean?
Let's say, let us replace it 0, 1 power. Let's take a error correcting code of block length 2b and rate half.
Yeah. So that's the concatenation will take the next step. That is, it will continue to remain linear. It will still remain linear. Or you need to say get it back to 0, 1. You can do that. That's what concatenation will do. But I want to say, but for concatenation, you need an outer code which has good distance. Let's first ask, does the outer code have good distance? Let's ask that. So what's the rate of this code?
Number of code words is 2 power 8 and the dimension is 2 power 8.
Yeah.
So 1 by 2.
So what have happened? It's the rate. Basically, it's
R by B.
the number of code words has not changed. The number of code words has not changed, but the alphabet size has changed by D. Therefore, it's the original rate.
R by B.
It's still diminished. By the way, I think I'm using R for two different things. So that should let me call that. I never actually use this. So just calligraphic R. I never actually use the. So the rate of this code is just R byte. It just diminishes by a factor. What's the distance of code? That's the most important. Once we notice these sort of linear codes, the weight of the distance of a code is the minimum weight the non-zero code word. You don't need for linear code, even linear by this definition. If a particular code is, because for how did you get minimum weight non-zero code word for linear codes? It's not the minimum distance between two distinct code words, but the minimum weight non-zero code word. We just took two code words, subtracted them, and said this is a non-zero code word. Subtraction is still a feasible option. It's only scalar multiplication is not a feasible option in this. Therefore, even for these sort of linear codes, the distance is the minimum weight non-zero code word. So how do we do this? Let's take a non-zero. Of course, if you put the zero code word there, what you'll get here is the complete zero code word, and that's the only way you will get the complete zero code word. Now, so let's take a non-zero code word here and ask how many locations here are non-zero. We'll witness at least one in the D blocks. So this is the question which we'll ask. So for this, we take. So let C belong to C be a non-zero code word. And let S exactly be those locations I in 1 to n. This is the left side. Let me just change that to n and n itself. A set of locations so that Ci is not equal to 0. It's a non-zero. I'm writing C1 over here, and these are the locations where it is 1, and here all it is 0. Now, every neighbor of this guy is going to be a non-zero element over here. So over here, this entire neighborhood, all of these guys are going to be. What I want to ask is how large is this neighbor? So I know so S. So notice that S, size of S is at least equal to delta times M. This comes from the distance of C.
What is the vertex expansion parameter of C?
We haven't. So we could have defined this in terms of vertex expansion also. But the reason I will do spectral expander is because for the AEL modification, for this particular code, vertex expansion is sufficient. In fact, for this code, all that is let's distance of C. So what do I need to show that P is large? If I show that every neighbor of size at least delta n has a neighbor of size at least beta n.
As a neighbor.
Every neighborhood of any set of size at least delta n is of size at least beta n. That means a code which has distance delta on the left hand side translates to a code which has distance beta on the right hand side. For this property to be true, all you need is this dispersive property. So for what the dispersive property is this following property. If every set S subset of n, so that mod S is greater than or equal to delta n, satisfies. So this is I'll call it a delta beta dispersive.
So the definition will be less than 4.
Huh?
So the definition will be less than.
No. Dispersive will be for every set this one. The usual dispersive, but the dispersive that I want here satisfies gamma S is greater than or equal to beta n. I'm not stating compared to that, yes. Therefore, if it is true for, this is sufficient if it's true for delta n size sets, because gamma of a larger one will only become larger. If this is true, then, so if this property were true, then this property were true. So what I'm claiming is G is delta beta dispersive and P is an n or n delta n code.
There is delta in.
Huh?
There is delta in.
And then EV and GC is a, so this is over 2. This is going to be, this also block length is n. Its rate is now r n by t. The rate is deteriorated. What I want to say here is beta n. The alpha beta is 2. Of course, where is this dispersive property? So we will prove, this is of course one way to finish off this code. Let's say if the underlying expander has this dispersive property, then we will be. But let's prove this dispersive property or what we want from the EML, expander mixing level. So let's define P to be gamma S. And what are we asking? We are stating that every neighborhood of, I want to claim, let's apply expander mixing lemma. To D and to S and D. And let size of T be equal to rho n. Okay. So what is the expander mixing lemma? We have to write down this two quantity. What is the expander mixing lemma? So you pick the left end point from S, take a random neighbor, and then what's the probability that the left end, pick a left end point at random and then a random neighbor of it. What's the property that this pair I and J has a property that I falls in S and J falls in T. So what is the, so now for this particular choice of S and P, what's the property that if I pick a random, if I do this random process, the left hand point is in S and the right hand point is in P. So what's a random process again? Random process is the following process. So let's just write down the EMF and then the probability Ij is in S cross T, where I is picked uniformly at random from now the left side. J is a random neighbor of I from the right side, minus mu of S times mu of T. This is less than lambda times some more quantities. Let's drop off all the other, they're all numbers less than 1, so this is all I will keep of lambda. So let's rewrite this. Let's expand what are each one of these are for this quantity. So what is, okay, this is easy to write. This is delta times rho. Mu of S is delta, mu of T is rho. What is that?
T is neighborhood comma.
Yeah. So once I pick
Yeah.
Once I pick the left endpoint, right endpoint.
A condition dot I is always empty.
Yeah, so this is just delta. It's just this is just delta. So it's just a property that I pick the left endpoint from S. The moment I pick it, the right endpoint automatic. So this is just delta into. So what we do have is this quantity is less than lambda. Or equivalently, 1 minus rho is less than lambda by delta. In other words, the distance of this new code, the distance of this code, the distance, hence that is distance of AB and another code. Is at least 1 minus lambda by delta. So this distance, you had an initial distance of, so this is where I will need to choose lambda to be.
To multiply this by delta.
No?
To multiply this by delta.
No. Because mod t is mod t is lower than. So this is the distance of the code. So the distance of the code. So I started off with a code which had distance from small delta. And suppose that the expansion was such that lambda was smaller than delta. So it was epsilon times smaller than delta. It is epsilon times delta. I'm getting a new code. Of course, it's over a larger aspect. The distance has grown from delta all the way to 1 minus epsilon. The distance is just enormously increased. So distance amplifier. So that's the I want to say. So that's the theorem of if G is a lambda spectral expander. Lambda being smaller than delta, then the distance of the AB and another code is at least 1 minus lambda.
And this can be an MDS code for large scale.
No, so for that we will need to understand how good the expander is also because
Order 1 square.
yeah, I haven't checked. So already the very next AEL modification will improve the parameters of this object. Okay. How am I doing with respect? Already shot. AEL is a small modification. So I'll finish it and wrap it. So is this construction clear? It's a beautiful construction. It takes codes of small distance, uses the expander, and gets a code of large distance. It's unclear what this large and distance, whether they are optimal in some sense, but it gets you some parameters. Now let's stare at this code. Let's stare at this code. Why did it lose on rate? It lost on. Now the question is, this construction is good with respect to distance, but it's bad with respect to rate. Rate is just falling by a factor p. And question is, can we rescue? Can we redeem this? We want to see if we can redeem the rate not falling. If you look at carefully stare at this code, what happened here? I put this code C1 here, then wrote it on the vertices and pushed these symbols along the edges to the other side. So you can think of this process in 2 steps. First, I had the code. I applied the D-wise repetition code on each symbol. So I had the code. I did one concatenation process from going from the vertices to the edges, and there I used the so going from the symbols were on the vertices, I went to the symbols on the edges, and then pushed the symbols to the other side from the edges. But going from the vertices to the edges, what was the process we did? If you look at it, this is exactly concatenation, a concatenation with the repetition code, the D-wise repetition code. We took out every symbol, we just repeated it D times, and it was this reason of concatenation with the repetition code that what causes the distance to go down so badly, because the concatenation with the repetition code is going to concatenation is a product of the rates, and you have the outer rate plus the inner rate. The concatenated code has distance, so the repetition code is rate 1 over p, and this is what. But should we get instead of using the repetition code, now you put a symbol here. when you're sending the D symbols out, why do you use the repetition code? Use some other nice code, take this symbol and use another code instead of the repetition code. Let's use another code whose output alphabet is D, but who's not the repetition code. And then send those D symbols across. So we could think of doing it. And that's basically what Alon-Edmonds-Luby idea is. Alon-Edmonds-Luby is the Alon-Edmonds-Luby modification. It's going to ask the above the ABNR construction. Construction can be viewed this way. It's code concatenation of C with the repetition, the device repetition code to move from vertices to edges. You use the concatenation and then push these symbols. The edges were now listed on the left side. Just push these symbols all the way to the other side. Correct. Why should you use the repetition code? This has horrible rate. Use a code which has good rate. So their idea is use a better code. Repetition. Then repeat. So say we use a small code C0, which what does it do? So think of it as it takes sigma to let's think of this as it takes. So let me draw the picture here. And there. So G, the ingredients are G as before is a deregular. Lambda spectral expander. This is code C, which is a set of n or n delta n, and let's assume this is all the alphabet Q.
Delta.
So some alphabet Q. We have this C1, C2. Now I'm going to have yet another code, C0. C0 is, and Q is, Q, think of Q as Q. C0 is a code going from 0, 1 to R, but that's called Q. So Q, 0, 1, D. That's the one. It's a code with D. R is equal to R naught. It's a code with D with R naught D and delta naught D. Therefore, C naught, now you apply C naught to it. So the way to do this will be to think of C1, C2, Cn residing here. To go to the edges, you apply the code C0 on each one of them. So it's an R symbol thing, you apply the edges, so that's how you go to the edges. And now this is pushed across and you correct them. Okay. So the AEN of GC and C naught is a code X sitting in 0, 1 to the P n. I'm not going to write this to code, so it's clear what it is. So that's the code. Is the code clear? So it's almost the same thing as think of the ABNR construction. ABNR construction, we had the code, we just pushed this, the code was on the vertices, and we just pushed that vertex symbol on the edges.
So we have R bits on each vertex.
We have R bits on each vertex.
You suppress C naught and then
You suppress C naught, you get D bits, and then push those D bits across. That's all. Previously, we pushed the same symbol on all the edges. Now you have R bits on each vertex. That was what, because it was Q was 0, 1 to D naught. You apply C naught, you get D bits, and push those D bits along the edges. That's the AEL construction. Fine. So what's the rate of this code? There is the only rate is what happens when doing the concatenation process. After that, nothing is lost. It's just recollect. Huh? So it's just RRC. Rate is just RRC. And this is where we are going to save from. This is exactly so. If C naught was the repetition code, this is exactly the previous construction, and R naught there was 1 over T. Now, what's the distance of this code?
Same.
No. The distance, you have to be a little more careful about this. The distance of this code can never be better than the smaller code, the delta naught. You don't expect the code to have a distance better than delta naught. Because what's the fraction of non-zero, guys? You can see over here is delta naught.
Yeah, delta naught and delta expansion there.
So this is the hope. The hope is the repetition code had distance 1, and the distance of the final ABNR construction is 1 minus lambda by delta. This basically C naught code will have distance delta naught, and the expansion will drop it. So the distance of this, what we'll show is the following. The theorem of AEL is the distance of the AEL code will be at least delta naught, which takes the distance from the base code, but it's going to drop by lambda by delta. It's exactly the same as one as before. And the proof of this, let's 1 minute. The proof is identical to the proof which we had before. So as before, take a non-zero code word. Take a non-zero code word. This is also everything linearity is preserved, but in this other sense that I said, take a non-zero code word. Yes, over here, size of S is delta n, and then size of S is delta n. What do you know about these guys? What do you know that these guys, these are non-zero symbols, when viewed as R symbols. Therefore, because the distance is smaller, each of them will have delta naught of their B neighbors being non-zero. So all that you know is and these TB. So let's say this. Let's C belong to C, non-zero code. C prime belong to AEL, be the corresponding AEL code word. S is those I in N such that Ci is not equal to 0. E is those J in N such that C prime J is not equal to. This is vector 0, vector 0. That's the R wise vector, this is the T wise vector. Let's say size of S is delta n, size of T is as before rho n. The same expanding mixing lemma statement I'm going to write. This is delta times rho as we had before. What will this be?
Delta.
Delta naught. Because you only know delta naught, guys. It's not 1 as before, but delta naught. This is less than 1. That's the same exact same rule. So 1 minus rho is less than lambda by delta. Lambda by delta.
Delta 0 minus rho. Delta 0 minus rho. Delta 0 minus rho is not
Delta 0 minus rho is less than lambda by delta. That's exactly the thing which I promised. Here is also a very nice construction. In all of these uses the power of the expander. Stop with this, I don't way too much. We will stop our discussion on expander codes and go on to the next topic, which is less decodable codes from Wednesday's lecture.
So even we are also, if we take lambda to be as good as possible, this does not achieve this.
There have been works to do this. I don't know of the topic.
It's only Solomon course these codes are in this.
It might be the case that you can achieve, go all the way to you can probably recover what Solomon achieves. I don't know. If this needs to be checked, I haven't done this.
Because currently only MDS codes are polynomial.
The only MDS code which you know of polynomial is.